All right, let's jump right into this. Welcome back to The Explainer. Today, we are uncovering the massive forces and the just incredibly precise engineering required to steer the world's largest ships. I mean, think about the sheer scale of a modern cargo vessel or a supertanker for a second. We're talking about massive floating cities carrying thousands of tons of weight, but their entire directional destiny, it literally rests on a single piece of steel at the very back of the ship, the rudder. So, how do you actually move that rudder against the crushing force of the ocean? Well, the answer is hidden deep in the ship's steering gear room. Let's break down exactly how this hydraulic muscle keeps global commerce safely on course.
To really grasp how critical this system is, we've got to start with one specific number, 45. By international maritime law, specifically the SOLAS framework, which stands for Safety of Life at Sea, if your ship's primary steering gear fails, your vessel must be back under control within exactly 45 seconds. And that has to be done using a completely independent backup system. Not sometime soon, not give us a couple of minutes, 45 seconds. That single number tells you absolutely everything you need to know about how seriously steering gear reliability is taken. It's the exact rule keeping that massive cruise ship you might take for a vacation from slamming into a concrete pier if a pump gives out. It's a ticking clock that dictates the entire engineering of the system.
And the reason for this insanely strict time limit is simple but severe. A ship that can't steer is a ship that can't avoid a collision. When you're navigating confined waters, high-traffic channels, or dangerous weather, losing your steering is an immediate, catastrophic emergency. The momentum of a massive vessel just doesn't stop. If you lose the ability to point your thrust where you want to go, you are entirely at the mercy of the water. So that rigid 45-second ticking clock, it is the absolute line between a minor mechanical fault and a major maritime disaster.
Okay, let's get into our first major concept, hydraulic muscle, and how it overcomes the ocean.
Think about it. How do you actually move a giant rudder against the ocean? A rudder traveling at speed through the water is experiencing just massive hydrodynamic resistance. The forces at play here are astronomical. You have to realize that no human being turning a wheel, and honestly no simple mechanical linkage of gears and cables, could ever move that rudder directly. The sheer water pressure against the blade would instantly snap a standard mechanical linkage like a twig. Because of those forces, we absolutely have to use hydraulic power multiplication. And that is exactly where the steering gear comes in. By definition, the steering gear is the hydraulic system that converts a helm order from the bridge, the captain turning the wheel, into actual physical rudder movement. It takes that electronic or mechanical signal and unleashes extreme hydraulic pressure to swing the rudder stock to whatever angle the bridge commands, and it does it quickly, with enormous, unstoppable force against that water resistance.
Now let's look at the beating heart of this hydraulic muscle. Part 2, pumping without reversing, using variable delivery pumps. Okay, this is a concept that kind of messes with our everyday understanding of machinery. In your car, if you want to go backward, you have to engage a completely separate reverse gear, right? But steering systems need to make constant micro-adjustments, left, right, with literally zero delay. They solve this using variable delivery hydraulic pumps. These pumps are constantly running, spinning in the exact same direction at the exact same speed the whole time. Yet they can instantly change how much oil they pump, and crucially, in which direction that oil flows. There are no clunky reversing valve gymnastics required here. It's all handled by smoothly adjusting the internal geometry of the pump itself. Let's look at the two brilliant designs that make this happen. First up, the Heal-Shaw pump. This one uses radial pistons arranged around a central control ring. By physically offsetting that ring's center relative to the rotating cylinder block, you change the stroke length of each piston, which in turn varies the flow. Reversing the offset, that reverses the oil flow. On the flip side, we have the swash plate pump. This one uses axial pistons that are pushed in and out by a rotating plate mounted at a variable tilt. If you steepen that tilt, the stroke length increases, pumping way more fluid. But if you tilt it back past the neutral center, the pistons actually move in the opposite pattern, entirely reversing the flow.
If that sounds a bit dense, just try picturing a wobbling plate balanced on a continuously spinning stick. If you tilt the plate deeply, the outer edges travel a great distance up and down. That represents your pistons pushing a massive volume of oil. But if you level the plate out perfectly flat, the stick keeps spinning, but the edges don't move up and down at all. That means zero flow. Tilt it the other way, and the flow completely reverses. It's just a beautifully simple and elegant way to get full proportional, reversible control from one continuously spinning pump.
So we've generated our high-pressure hydraulic fluid. Now let's see how we actually apply it. Part 3, rams and vanes, and physically turning the rudder stock.
There are basically two primary ways to turn the rudder stock. First is the ram-type steering gear. This uses massive hydraulic cylinders, the rams, that push in a straight line against a really clever mechanism called a Rapson slide. The Rapson slide basically takes that straight line push and mechanically converts it into the rotary motion you need to twist the rudder stock. The second type is the rotary vane steering gear, which is a lot more direct. Here, vanes are mounted directly onto the rudder stock itself, enclosed inside a heavily sealed circular housing. When you pump high-pressure oil into the chambers on one side of the vanes, it directly rotates the stock. No separate linkages converting linear to rotary motion required.
Now, for the real massive heavyweights, we often rely on a 4-ram system. This setup employs 4 separate hydraulic cylinders grouped right around the rudder stock. The absolute brilliance here is in the routing. A pump will draw fluid from 2 diagonally opposite cylinders and discharge it into the other 2. This gives you incredibly high torque output to swing those massive rudders, but even more importantly, it provides exceptional flexibility. If one cylinder, or a pump, or a line fails, a special control valve block lets the crew isolate the broken parts. They can just continue steering the ship using 2 port rams or 2 starboard rams, or one of the backup pumps. It is literally redundancy built upon redundancy, ensuring safety is never compromised.
Which brings us right back to that ticking clock we started with. Part 4, the twin system failsafe, and beating that 45-second clock.
We actually need to bust a major myth here. A lot of people hear the 45-second rule and picture a crew member realizing there's a problem, sounding an alarm, sprinting down multiple decks to the steering gear room, and physically throwing some giant lever to switch to the backup. Yeah, that's entirely false. The 45-second rule is an automated system design requirement. The backup steering system isn't a manual switch-it-on process. It literally has to be capable of detecting a primary failure, like a massive oil leak, and taking over essentially all on its own.
So how does it actually pull this off? Let's walk through the automated changeover sequence. Step 1. Imagine a severe oil leak happens in the active hydraulic circuit. This immediately causes the oil level in a monitoring float chamber to drop. Step 2. As that float drops, it hits a proximity switch. Boom! This instantly triggers a bridge alarm and fires a solenoid valve to isolate that faulty, leaking circuit so you don't lose any more oil. Step 3. The system automatically shifts electrical power to the backup pump motor and opens the self-closing lock valves for the reserve circuit. Step 4. The backup system pressurizes and full rudder control is regained. This entire logic fires off with automated precision, completely finishing before that 45-second clock runs out. And because this automated logic is literally the only thing standing between a ship and a collision, pre-departure testing is absolutely mandatory. Steering gear testing is an essential checklist item before a ship ever leaves the dock. The phrase, "we'll fix it once we're underway," is never ever an acceptable fallback here. A total steering failure at sea, especially in a tight channel, is an immediate grounding emergency. It's not just some maintenance inconvenience you can log for later. The strict weekly safety routines and pre-departure checks are what convert this theoretical safety net into a genuinely reliable reality. When you really step back and put it all together, the magnitude of what's happening below decks is just awe-inspiring. Between the thrust block that physically pushes the massive hull forward and the steering gear that wrestles the ocean to guide it, you are looking at the ultimate unsung heroes of global shipping. These hidden hydraulic and mechanical marvels tirelessly work together day and night across oceans just to keep global commerce moving safely and efficiently. But, mastering propulsion and steering is really only part of the battle of surviving at sea. With propulsion, shafting, and steering all covered, the next natural question we have to ask is, what happens when something goes catastrophically wrong to threaten the very survival of the ship itself? How do you fight a massive hazard when you are literally thousands of miles from the nearest fire department? Well, that brings us right to the critical realm of fire and safety systems, which is exactly what we're going to be tackling next. Thanks so much for joining me for this explainer, and I will catch you in the next one.